Okay, so any object that can be deformed, have its shape changed, and then return to its original shape is said to have elastic properties. So this has elastic properties because I can change its shape, but then it can go back to its original form. Okay? This has elastic properties because I can change its shape, but it goes back to its original form. Potential energy, kinetic if I let it go. Okay? So, items with elastic properties, things like elastic bands, a pole vaulter's poles, springs, slinkies, they all have that elastic potential energy. So let's just draw here. Like our slinky kind of thing, draw 4 loops. This is its original position. Let's refer to this as equilibrium. So go / equilibrium. So kind of just like with bio, when our body had to maintain homeostasis, we think about kind of that property or that state throughout all of science. So this is called equilibrium, where it's just it's at kind of a resting state, or it's at its original resting place state. So either we can stretch it, and it's going to be longer. Okay? Now for some springs, you could compress it even more. We can't really compress that slinky much more, but some springs you can. Both of these states are stored energy. So both, you can spell. Both of these are kind of our potential energy. Once it goes back, it will release kinetic energy and then go back to its original or equilibrium. So if it can't go back to its original, it doesn't have elastic properties. So while the object is deformed, whether either being compressed or stretched, it has stored energy until the object is allowed to bounce back to its original position. This is called specifically elastic potential energy. So we've done a lot of gravitational and potential energy, so this is elastic potential energy. So we can actually calculate it. If you recall kinetic energy, the formula for kinetic energy is EK equals half mv squared. Well, we can calculate the stored potential energy of an elastic using kind of a similar formula. And we call it EP equals half kx squared. Now K is the spring constant for the object. So it's like how hard is it for me to move the slinky? That's the slinky's spring constant. Okay? So it's like, how hard is it? How hard is it to move the spring? That's kind of like how I think about it. Now, this slinky, no matter which way I twist it, throw it around, up, down, stretch, compress, it's always going to have the exact same spring constant. Unless I melt this slinky down and put some metal in it or do something crazy, its spring constant will always stay the same. Okay? Because this is how it's made, this is the material it's made out of, this is how it's designed, it will have the same spring constant. Unless you change something physical about it, it stays the same. So what stays same? Spring constant. Is the spring constant of this slinky And the trampoline spring the same? No. So it's a lot harder to stretch a trampoline spring, right? Like, have you ever tried to put a trampoline together? Have you done that? Has anyone done that? Then you get your, oh, there we go, okay. So it's hard, like, if you attach the spring to the netting and then you have to bring it to the frame, like once you get a way around, it's hard, right? It's hard to pull it. So the spring constant of that trampoline spring is a lot higher because it's a lot stronger. It takes more newtons per meter to move it, okay? So this unit, note, newtons per meter. So I would highlight or circle that, newtons per meter. Our EP is joules, which makes sense because it's energy. So regardless of what type of energy we're talking about, it's always in joules. Just like with force, it's always newtons. Okay? And our X is the amount of expansion or compression in meters. So how far it's been stretched or how far it's been pushed in. Okay, remember energy is scalar, so you don't have to include direction with these types of questions. Now, here's a new law. Hooke's law explains the force needed to expand or compress elastic objects depends on the amount of expansion or compression. So this is Hooke's law. So circle, highlight that one. Now let's see. Take out your data sheets. Now, under dynamics, you should see Hooke's law. So under dynamics, you should see Hooke's law. And then under momentum and energy, you should see the EP equals half kx squared. Okay, so you do have both of these formulas here. You don't have to memorize them, but you do need to memorize the units. Okay, you need to know what the units are. So this is Hooke's law, where Fs, the force of the spring, is equal to the spring constant multiplied by the amount of expansion or compression. So taking those similar properties of work, but we're just looking at force. So the spring constant K varies for each type of spring. So each type of spring. And is a measure of how stiff a spring is, or how hard it is to pull it apart, like I was saying. The larger the spring constant, the stiffer the spring, okay? So just like I was saying, that trampoline spring is going to have a high K, because it's hard to pull apart. Yep?
So in that formula, if you have a negative K value, does that mean it would be positive
In what formula?
in the formula?
Oh, if you have a negative K, would it be positive in the formula?
When you put in a negative value?
Yeah, it should be. We don't really see the negative applied too much. We'll do the examples and then if your question isn't clarified. Yeah. Okay, good. Let's read this first. Okay, the negative sign in the formula simply implies that the force pulls back to restore the spring to its original position. This force is often referred to as the restoring force and is always pulling back. So actually, yeah, to answer your question, we don't use the negative really in the formula. It's just saying the force to pull back. So it's like your vector quantity, that you know that your spring is always pulling back. Okay, let's go to the first example.